start. Just a second over here. I hope everyone can hear me okay. Hello and welcome everyone to use case number 4 of the Data Lift number 3 event presented to you by the AI Guild. I'm your host for today's session, Felix Großmann. I'm a junior data scientist and also a member of the AI Guild. Before we start, just a few technicalities. This session will be recorded and might be uploaded on YouTube later on. So please only switch on your video if you are okay with that. Please keep yourself muted, but feel free to post questions you have for our speaker in the chat at any time, and we'll go through them after the presentation. You can switch on the side-by-side view while the presentation runs. That way the thumbnail of our speaker won't cover any of the slides. Okay, with that out of the way, let's not lose any more time. Our speaker today is a data scientist and instructor at Propulsion Academy in Zurich. And I'm very excited to hear his talk about statistical health monitoring of manufacturing machines, from sensors to insights to deployment. A very warm welcome to Badru Stanicki.
Thank you, Felix. So I hope you can all see the screen right now. So dear fellow members and guests, welcome to the session on statistical health monitoring for manufacturing machines. We have the chance today to go together on a short journey from sensors to insights to deployment. But don't worry, we will be back for lunch. So before we start, a few words about myself. So as Felix mentioned, I'm a data scientist and instructor at Propulsion Academy. My background is actually in physics. And after working in scientific programming, I joined around 2 years ago Propulsion Academy, first as a student, which helped me to make this transition into data science. And since then, I have been involved in coordinating the data science program as program manager, and now I'm focusing more on external consulting projects and working as an instructor. What do we do at Propulsion Academy? Our main focus is actually on education. So we have 2 so-called boot camps running, which are intensive courses for 3 months. One is in data science, another in full stack. And in this area, we already have graduated more than 300 students. One special thing about us is that we offer for all our students the possibility to work in a capstone project directly with a company from our network. So we have already delivered more than 50 data science projects by doing that. Here on the top, you see our team, but we actually have even a bigger network, since we have a strong interest in bringing always like the industry relevant tools and topics. We also have more than 20 external instructors, which are experts in their respective fields. Besides this, we also teach at universities here in Switzerland, and we also offer corporate courses. But that's not all. We also have a department for a consulting project. So besides the capstone project, we also offer our service to other companies. And actually I will present today one of these corporate projects. Last but not least, we also try to support local startups. Some of them were actually created by former students of us, and we're supporting them by building prototypes and also with our network. The project I'm going to present today actually started as such a capstone project. So after 2 months of training, we had a group of 2 students working for 1 month on this project for our client. And actually this time was only enough to explore a small space of the whole project. Since the project was interesting for our client, and also we think that it's promising, we continued with a 5 days proof of concept. And based on the findings from these both projects, we decided together with our client to create a data product for this to solve one of their challenges. The actual project then took around 3 months, was mainly implemented by myself, and recently was deployed, and now we're in the phase of monitoring and improving this data product. I can't get into the very details of our client and also the product itself, but to give you a context, you should know that our client for this project was a world-leading producer for manufacturing machines, and these manufacturing machines are mainly used in the automotive sector. So their customers have the requirement of having a high production quantities, and also they are very sensitive to defects during productions. And for that reason, our client started already some time ago a strong initiative towards a more data-driven production process. This consists mainly of 2 goals. Like, one goal is to detect abnormalities during production process. So if their customers produce parts, it will already track during the production if there's some abnormal behavior, and then these pieces which have produced can be removed from the further production process. The other part is that they try to detect defective machine components. So if the machine itself has a problem, then they can react to that. Our focus was on the detection of defective machine components. So we are here in the space of data-driven maintenance. Before getting the details, I just want to give you a broad overview about the different approaches of maintenance. Let's start with the classical maintenance. Classical means we don't have any further data available about the state of the machine. The very naive approach here is to go with reactive maintenance. Reactive maintenance means simply not doing anything till their failure happens at the machine. The problem is here, usually you never know when this will happen, and it can cause a lot of cost, not only due to the repairment of the machine, but also due to the unavailability of the machine. A bit of improvement regarding this is to go with scheduled maintenance. Here, the idea is to have on regular intervals parts of the machine repaired or also being replaced to prevent some of the failures. But still, a failure can happen since you can't exchange all the parts on a regular basis, and you have the same problems as before with reactive maintenance. A bit more intelligent approach is data-driven maintenance. This requires to have some information about the state of the machine, so it needs you need to install some sensors in the machines. If you have this, you can track for anomalies in the behavior of the machine itself, and only then react with the repair, and by that ideally completely avoid potential failure. To show you a bit the advantage of this, we can look into this graph. So what you can see is that on the very right side, you see the approach of reactive maintenance. So you have very high repair costs. On the left side, on the opposite, you can reduce the repair costs, but you will have a lot of cost for preventing failures. While the optimum is somewhere in between, and this is only possible if we have some information about the state of the machine. Another extension to that is the so-called predictive maintenance. I assume most of you have heard this already. So the difference to condition-based maintenance is that if there's an anomaly detected, it might be that it's not really required to react immediately. So you can use, for example, a machine learning model to predict the estimated lifetime of the machine, and then only react before the potential failure happens. So this enables you to even reduce further the costs for repair. Let's look a bit more into the scenario of our client. So I can't use the exact scenario, so I'm showing you some hypothetical scenario. But you can imagine, like, every complex machine has a lot of multiple components, and any of these can degenerate over time. And our focus for that reason was to assess the status of these individual components of the machine in regular intervals, with the goal of creating then a health score for every machine component, and as well a global health score for the whole machine itself. The advantage, the benefit of this is that this allows to have a dashboard which can visualize the scores for the components in the machine, and then the machine operator can react to this. And as example here, if you consider this bicycle a machine, you could have potential failures at the tires. You could also have at the chain, and if any of these happens, the whole bicycle won't be functional anymore. The main, the most important part here, which is the difference to the classical maintenance, is the data which this is based on. So our client already did a strong initiative to bring a lot of powerful sensors into the machines. And for that reason, there were a lot of signals available for each component. And these signals were either like scalar data, for example, what you see here, that could be a temperature, which is tracked over the time. But we also had a lot of spectral data available. So here you see such a spectrogram, which is also over the time, and you have the frequency. An example, for example, is if you have an acceleration sensor in the machine, you can track the vibrations at certain frequencies. And this is usually a very good indicator of the state of the machine, and can show whether very specific problems occurred. Let's look a bit on the deliverables of our concrete project. So the task here was that we process the data from all these sensors. So one component has a lot of different sensors. This could be the scalar, could also be the spectral data. Out of this, we had to generate one health score per component. And this is then done not only for one component, but for all the components of the machine, and in the end aggregated to one global health score per machine. And of course, things are never really as straightforward and easy as one would like. The main problem here was that we haven't had any labels available. So there's no labeling about whether the machine is working properly, whether there's a failure, what kind of failure happens. And even worse, like the type and the number of failures was not known in advance. It turned even out that there was only a very few number of failures, since the machines were very reliable. So typically they maybe have one serve failure every 3 years. So all this led us to the conclusion that we can't go here with classical machine learning, like, for example, training a supervised model on it. For that reason, we chose a more basic approach. So what we do in the end is that we automatically estimate the typical distribution for every sensor measurement. That can look, for example, like this. So we take a range which we take as reference, and based on this, we calculate the typical distribution. And then we run a statistical analysis to determine the deviation from this range. For example, like this. And if we exceed a certain value here, then this would trigger a warning for this specific signal. And these signals then are aggregated and they lead to the health score for the machine. The last part I want to talk a bit about was the deployment. Here the main thing to consider was that our client already had an existing infrastructure in place. So that consisted of a multitude of machines which were equipped with all the sensors units, and they are transferring the tracked data into cloud warehouse. And what also was in place is already the web application, which allows their customers to inspect the machine status and also to monitor the production process itself. And our task was to integrate our system into this. How we solved that in the end is that we added this like health monitoring service, which then was deployed also in cloud server. And we designed a way that it's completely decoupled from the web apps. So the web app is only reading data from the warehouse, and our health monitoring communicates only with the database. So it will automatically check whether there's new data available for a certain machine or a certain component. And as soon as this is the case, it will run our algorithm with the evaluation of the health score and write them back these values into the database, so that then this will then be visualized in the web application so that the operator of the machine can take action if there's a warning triggered. What else could be done in the future with the project? There's quite some potential. One thing we could extend is that we can compare sensor signals across machine. Like right now, we track for anomalies on individual machines, but as soon as there are more machines join the system, we can actually learn from other machines the typical behavior and apply that for machines which may be newly joined the system. One advantage of this could be that there could be the unlucky case that a machine from the beginning does not function properly. And this could then be immediately noticed if it's compared to other machines. And of course, there's also the potential for predictive maintenance, as I showed before. This would imply some more effort, since it would require some labeling. It would also require that we have a bigger set of machine failures from which we can learn, and then try to predict the usual lifetime after an anomaly detection. I just want to mention here again in the end what I already showed you in the very beginning. So at Propulsion Academy, we have this concept of capstone projects, which we conduct with our students. And this is a great opportunity for companies to explore projects, ideas which they maybe haven't had the resources yet. So I can imagine that maybe for some of you or for the companies you're working at, this might be interesting. The very nice thing is it's completely for free for companies. The only requirement is that you define the project requirements, usually together with us. And from our side, then we are selecting students which fit to this project. Usually we consider their background. And when we have a team for the project, we also supervise the project. The duration of the project itself is 4 weeks. And one requirement is only that from side of the company, that during the project phase, there's around 1 meeting a week to follow the progress and also bring in the domain knowledge. Yeah, thank you a lot. You're very welcome to connect with you. Also, maybe check out our webpage for Propulsion Academy. We are based mainly in Zurich and also soon expanding to Munich. And we're always very happy to get contacted and to help you.
Thank you so much, Badru. That was awesome. And very insightful. I really like that idea of your students getting some hands-on experience on real life scenarios. That must be super valuable for them. Okay, let's jump straight into the questions. We got a couple of minutes left, so again,
sure, I'm happy to answer.
You can post any questions you have for Badru in the chat, and we got only a couple minutes left, but maybe we can answer one or two questions. I see our audience is still a bit shy today, so I'm just gonna start with one question that I'm usually very interested, because datalift is all about getting projects production ready, right? And I was wondering what the most time-consuming or tricky tasks were when you were trying to get the project production ready.
Okay, yes, specifically for the production. So one of the biggest challenges there was that we didn't have any access directly to the system of our client. So they had all this in place. But so we worked with a development database. And then also when we had to install the system there, basically, yeah, in the end, we did it then via remote connection, and I instructed them what to do. So it worked surprisingly well in the end, but that was a bit the thing. Yeah, okay, how do we integrate this thing? And I think we found a very good solution by like almost completely decoupling it. And then it worked surprisingly well.
Great, cool, yeah. I saw that in the presentation. That looked really nice. And maybe yeah, we got time for one or two questions now. Some come in. So Guillaume asks, what did you use to create your web app?
Yeah, so the web app wasn't created by us. So they have already like a product where they provide value for the customer. And so the service that we added is like an extension to that, which gets like enables new functionality in this web app. So it was more about to integrate this. And actually, yeah, what the thing was, we had to coordinate things. So basically they pictured us, okay, what the added value would be for the customer and how the web application could look like. And then we designed basically the algorithm which is doing the calculation in the background.
Oh, I see. Okay, cool. I see now a couple of questions are coming in. Let's see. I think we got time for one or two more questions. So I'm just going to pick the next one. Davai asks, what kind of models are usually good for determining underlying distribution and detecting anomaly?
In this case, we don't have so many really like modeling. It's more about creating indicators which characterize the signals. For example, you had to boil down the frequency spectra into indicators, which we can track over time. And then how to say, looking at distributions, in this case, we solved relatively straightforward that we look, okay, what's the typical range of the values, and then we looked like some multiples of the standard deviation, something like this. And there are different things to optimize and so on, filtering and so. But the approach is more based on statistical distribution, not so much that we need to really model.
I see. Okay. Okay. The last question. I'm sorry, we don't have time to answer all of the question, but feel free to contact Badru. I'm sure he'll be happy to answer all of your questions, even after our session today. So I see one last question here from Shirley that I find very interesting. What statistical analysis did you run to estimate the typical distribution?
Yeah, as I said before, like we mainly calculated indicator to describe the signals.
All right.
And then we look for the typical range and how much the new signals deviate from that, and we kind of normalize this in a way that we can create the scores, and then the score, which finally comes out, basically describes how much the whole how to say the whole all the signals together, how much they deviate from a normal machine state.
I see. Awesome. Well, that's all of our time for today, folks. So I hope you enjoyed the event as much as I did, and make sure to check out the promo for the datalift ebook, because it's free for today. I'm just going to post the link again in the chat. So make sure you get the ebook version today, because it's free. You might need to copy that link, but okay. Thank you again, Badru, for being our speaker today and for answering some of our questions at least. And thank you everyone for joining us, for participating. I hope we see each other again for datalift number 4, which is in March 26th. It's a Friday, I believe, again at 11 a.m. Until then, take care and bye-bye. Oh, one last thing. I'm going to post the datalift number 4 event link here, so you can go ahead and register if you want to. Okay.
Thank you, Felix.
Thank you, Badru.
Thanks to everyone for joining.
See you guys. Bye.